Welcome to Part 5 of the module on Gang of 4 and POSA 1 pattern examples that apply to concurrent and network software. In the previous parts in this module, we've described a bit about the Gang of 4 and POSA 1 books, talked about the history that went into making those books, and described how many of the patterns in the books are relevant for concurrent and network software. In this module, we're going to be following on to some of the discussions we had earlier using an Android application in order to illustrate how the observer pattern from the Gang of 4 book can be applied to simplify certain aspects of that application. Quick recap of the application. We have an activity that's run in response to a user clicking a button, providing a URL. That activity uses either the proxy pattern and broker pattern or the command processor pattern to communicate with a download service, which talks to a web server, which downloads the image content requested in the URL. That content is stored in the file system. Some metadata is put in a content provider to describe things like the time it was downloaded and size information and so on. And finally, the Uniform Resource Indicator, or URI, is passed back to the application activity, where it's displayed to the user. What we'll be doing now is talking about how the observer pattern can simplify some parts of this design. The previous parts we've discussed have focused on sort of systems programming and application level use of systems programming features to implement various patterns in support of the application. This particular example is going to dive down more into the system infrastructure and talk about how the observer pattern can be used by Android itself in order to simplify certain kinds of things that many applications need to be able to do. Here's the context. Smartphone platforms like Android and iOS and so on keep track of lots of system-related status information that may be very useful to applications. For example, these phone platforms work in conjunction with the hardware to detect when the battery is running low on juice. And they have ways of being able to report this up to interested parts of the system, applications, system services, and so on. The problem here is severalfold. First of all, it's probably the case that multiple apps and services may be interested in this system status information. For example, in Android, the phone app is interested in the battery being low, as is something called the system server, which keeps track of some of the status information. There's a couple of ways to do this wrong. One way to do this wrong would be to tightly couple the status information that resides in the system with specific knowledge of particular applications and hard code those things in a way that would be very brittle and difficult to change. Another ineffective way of providing a solution would be to have the applications, activities, system services, and so on repeatedly poll the underlying Android infrastructure asking for information about battery status. That would be inefficient and would be a big waste of CPU time and would again be brittle and tightly coupled. So what's a more effective way of designing this? Well, what we'd like to do is come up with a way to automatically notify all interested applications that depend on system status information when this information changes. So as you can see here, we have some kind of notifier and some way of being able to have the various applications and services subscribe, and then when something happens, like the battery goes from fine to low, we can notify the interested parties. So let's talk about how we might do this in Android. Well, the first thing that we could do is we could make various parts of the phone app and the system server be broadcast receivers. A broadcast receiver is something in Android that can be notified when some event occurs. And what specifically happens is that when something of interest happens to a broadcast receiver, Android will call back the onReceive hook method, which then does something about it. We would then go ahead and use the register receiver method that's defined on the Android context object to register or attach the broadcast receivers, indicating what they were interested in. In this particular case, they might be interested in the action battery low intent. And finally, a service that's part of the Android infrastructure called the battery service coordinates with the hardware, and when it detects the battery has gotten low on power, it broadcasts an intent that says the battery power is low. And the Android Activity Manager service then turns around and delivers that intent to all the interested broadcast receivers by arranging to have their on-receive methods called back. If you take a look at the way that this actually works in the Android implementation, you'll also find that the Android intents framework uses other patterns we've talked about, such as proxy and broker, in order to do all these various steps. Well, once again, it turns out that this arrangement of classes and objects is not just random. In fact, it conforms to one of the classic design patterns, the observer. Observer, like proxy, has appeared under different names in different contexts, different books. It appears as an object behavioral pattern in the Gang of Four book, and it also appears as an architectural pattern in the POSA 1 book, where it's given a slightly different name. It's called the publisher-subscriber pattern. And it turns out that observer and publisher-subscriber are a bit different in some aspects, but they can be used in much the same way. We'll be focusing on observer in this discussion. Later discussions, we'll be talking more about publisher-subscriber. The intent of the observer pattern is to define a one-to-many dependency between objects so that when one object changes state, all the dependent objects are automatically notified and updated. And you typically want to use this pattern when whatever you're developing has two aspects to the abstraction you're trying to provide, one dependent on the other. Also, where a change in one object requires changing or notifying untold others, where you don't know in advance how many there are. And finally, where the objects should be loosely coupled. They shouldn't have to know about each other in terms of specific names, specific behaviors, even specific programming languages they're implemented, and so on. There's a number of different ways to structure this pattern. The particular way we're looking at here is based on the Gang of Four perspective, but be aware that there's lots of other ways to do this pattern that are still observers that don't slavishly follow exactly this structure. Typically what you do with observer is you have a subject role that has a couple of methods that allow you to be able to attach and detach instances of observer, usually referencers or pointers. And these observers themselves in the Gang of Four model are implemented as abstract classes, which is to say that they have some kind of abstract method or pure virtual method, often with a name something along the lines of update or onChange or onReceive or whatnot. And this hook method can be overridden by subclasses that inherit from the observer base class. When you use observer, what you typically end up doing is you create concrete observer instances, attach them to the subject, and then when something interesting happens that involves changing state, you call notify on the subject. And what notify does is it iterates, most likely using the iterator pattern, through the set of observers calling update on each of them. And when the update hook method is called back, in the concrete observers, they can then do their thing. And they can do their thing in various ways. They might go ahead and make a method call back to the subject or some other source of data to find out more information about what's going on. Conversely, the update method itself might pass along the information of what's changed or a hint to what's changed to speed up that lookup process. Once again, though, there's many different ways to implement this pattern. This is just a common way to look at it. Here's a view of the dynamics of the observer pattern. As you can see here, we have concrete observers. We have multiple concrete observers that go ahead and attach themselves to a subject. And when the subject is notified of changes, it turns around and dispatches the update hook method on all the observers that are registered with it. So let's take a look and see how we might implement this pattern in Android. I went to the Android source code and just extracted little snippets of code that you can find if you poke around in the source. For example, there's a couple of files called status bar policy and phone app, which are part of the main Android release. And these application classes register intent filters for various types of things they're concerned with. In this particular case, they might register for the intent action battery low, which says, please call me back when the battery gets low. The battery service implementation in Android works with the hardware, figures out the battery has become low. As you see here, it creates an intent, sets its action to be action battery low, and then it broadcasts that intent to any and all interested broadcast receivers. Looking at just one small little snippet here, here's a piece of the phone app code, which is a broadcast receiver, and its onReceive hook method is automatically called back by the Android Activity Manager service when a broadcast intent is sent out that corresponds to the battery being low. And it takes a look, figures out what kind of intent it got, and then it takes the appropriate action. In this case, it will send some kind of notification message to the display indicating to the user that the battery has become low, and they probably should plug in to recharge at this point. There's a number of interesting consequences of applying the observer pattern. Some of the pros of applying the observer pattern is that it allows the subject and observers to vary independently. It's inherently modular. The observers don't have to know about each other. You can make different kinds of changes. You can customize observers. One observer can behave in very different ways than another observer. In the particular case of Android, we saw that both observers, both the phone app and the status bar app that's part of the system services, they both end up displaying dialogues to the user, but they could be slightly different dialogues. And the context in which they're called is also quite different as well. One is called from the context of a phone operation. The other is just called to update the status bar to indicate that the battery is going low. Moreover, you can make changes. We can come along and add new applications, new services to Android that might want to handle these in different kinds of ways. For example, you might write an application that would be adaptive, or a service that was adaptive in response to the knowledge that the battery was running down. As the battery gets low, you might dim the screen. You might run the processor at a lower speed to be able to conserve battery power. You might make fewer communications across the network, once again, to try to conserve battery power. And you can make all these changes without breaking or changing already existing observers that have their own purpose, their own intent for existing in the observer pattern. There are, of course, some downsides here as well. One of the problems is that observers don't always know about each other, which means that you can end up in situations where a lot of extra communication takes place that might not otherwise be expected because you have observers that don't know enough to realize that they're redundantly broadcasting information to each other. Let me give you a common example from about 20 years ago. If you went back about 20 years ago, people were a lot more attuned and sensitive to receiving emails they didn't want to get. Nowadays, we're so inoculated to spam that when we get an email that we don't want, we just delete it. We don't think about it too much. But back in the old days, when you got unwanted email, you tended to recognize it, and many people would respond very aggressively when they got unwanted emails. So I'll never forget, one time I was, about 20 years ago, I was a graduate student, and I somehow ended up on a mailing list, and I received some mail on the mailing list that I didn't really want, and clearly all the other people on the mailing list didn't want either. Because instantly, the minute they received the email on the mailing list, most of them replied back to the mailing list saying, please don't send unnecessary emails to me anymore. Well, of course, the mailing list was set up to use an observer-like structure, so all the other recipients received all the emails saying, stop wasting time sending emails. So it was an example of what we sometimes call a notification storm, where everybody was just clogging up the email system with unnecessary messages, telling each other not to send unnecessary messages. And the reason that was happening was people didn't really understand that they were sending to a mail exploder that was sending the information and distributing it out to all the other observers who are subscribed to the mailing list. This leads to another potential downside with Observer, which is too much update overhead. Even if you don't go as far as my email broadcast example, there may be situations where you're getting notified about events or intents or other kinds of actions that you really don't care about, and you just have to filter them out in your Observer implementation. For example, if you look back on the battery voltage example for the broadcast receiver, one of the things the broadcast receiver does is it checks to see if it got an intent it really wants to deal with, because it's going to be subscribed to lots of other events in well. So what are some implementation considerations to address some of these issues? Well, one thing we have to deal with, of course, is how do we map subjects and observers to each other? If you're co-located in the same address space, you would probably use some kind of data structure, like a linked list or an array of pointers to base class objects, or an array of references to objects that you could then iterate through and dispatch by just making a method call, calling update, or onChange, or onReceive. In contrast, if you're talking between subjects and observers that are in different processes, as is often the case in Android with its broadcast receiver mechanism that's part of the intents framework, you're going to have to do some more things. You're probably going to have to use a broker and some proxies in there in order to be able to communicate back and forth. If you're talking about email, then you're probably passing messages between various kinds of servers. So the subject-observer mapping is quite varied, and there's no single way to do it, which is why you have to be very careful not to think that the diagram you see in a pattern structure picture is the canonical and only way of doing that implementation. Some other considerations: dangling references. What happens if an observer goes away, either because it's done but forgot to detach itself, or because something got shut down and nobody notified the subject? A good example there would be mailing lists. If you ever have maintained email lists, you know that oftentimes people subscribe and then they change jobs or they change identities and their emails are no longer valid. So you've got to have some way of handling that gracefully. The worst way to do it, of course, is to have your system crash because it calls an observer that no longer exists. It's a so-called dangling reference. Some other considerations that are very important: the update protocol. What happens when the subject calls update on the observers? There's a variety of ways to communicate information between the subject and the observers. One way is to make the update very lightweight, just a method call with no parameters at all, and then require the observer or observers to pull any necessary information from the subject or from some other database that they may need in order to do their update operation. Another way to do it is to pass some information with the update. Pass it as a parameter. Pass it as some kind of URI or some kind of indicator into a database. Some way that you allow the observer to get the information more quickly so it doesn't have to go out and pull something. So that's more of a push-based model. Once again, there is no one-size-fits-all solution that's always right. If you have very lightweight mechanisms for updating observers, then you may incur a fair amount of overhead to pull the data later. If you use a more heavyweight mechanism, then observers may get information they don't actually need a lot of the time. So an architect is really necessary to sit down and think carefully about the implications of different models that you may need to do. Another thing that you have to consider is whether or not you want to have some kind of filtering mechanism implemented when you attach an observer to the subject. This is one place where the publisher-subscriber variant of these patterns is often different from the very straightforward observer approach. With publisher-subscriber, it's almost always the case that you're going to have some filtering put in there so that not all observers receive all of the messages, all the updates that are generated when a subject is notified. And we'll talk more about that when we talk about the publisher-subscriber pattern later. But the point here is that this is a very rich pattern. Knowing the structure and core interactions of the pattern are just the starting point for figuring out how to use this pattern effectively. A little bit later in the course, we'll talk about some of the ways in which this pattern gets combined with other patterns to be able to solve broader, more systematic and strategic aspects of design. There are many known uses of the observer pattern. Pretty much every user interface framework, from Smalltalk onwards has used this as a way to be able to update windows and displays in different ways. If you've ever played around with Excel spreadsheets, you know that you can attach different observers to cells in your matrix. And when you make changes to the data, you can have pie charts, histograms, bar charts, and so on vary independently from the same data. Lots of notification mechanisms, things like Android intense frameworks, other notification mechanisms in general tend to use this kind of an approach. And this interaction of observer and observable is actually baked into some parts of the Java class library. So Java programmers will find this very convenient and intuitive. So to summarize this module, the Gang of Four and POSA 1 patterns promote reuse of many microarchitectures that arise in concurrent and network software. We've seen patterns like broker used in conjunction with other patterns like proxy. We've seen complements to broker and proxy like command processor, which we can use to solve various issues in concurrent and network software. We saw the use of the observer pattern to solve some low-level issues in Android systems, monitoring of status information, and so on. And these recurring architectures are very powerful to structure and document what you're doing, as well as to be able to figure out how to apply the same techniques when you build your applications or you build infrastructure that's different from the things we've been talking about, but you can still leverage the same insights. These patterns are also extremely valuable to help teams communicate with each other more effectively. Once you understand the concepts, and once you can use a term like observer or broker, and have everybody on the team have roughly the same sense of what the structure is, what the dynamics are, what the consequences are, and so on, you can work together more effectively because you don't have to get bogged down in a lot of low-level implementation considerations in the design and architecture phases. Very, very valuable ways to communicate more effectively. As we've seen, even in the small discussions we've had of these four main patterns, they also open up a window to many other patterns that are needed to make them be used most effectively when we build real systems. Many of the patterns we've seen in the Gang of Four and POSA 1 are relevant for concurrent and network software, but you have to be a little careful because not all the patterns were initially designed thinking through all the forces and all the considerations and constraints that arise when you use them in concurrent network software. In one of the earlier modules, we talked about the singleton pattern and how you have to be careful when you apply it in multi-threaded or concurrent environments because some of the issues having to do with memory models and race conditions that might otherwise arise. Other patterns, especially in the Gang of Four book, were not necessarily designed with concurrency in mind, so you have to think carefully before you apply them. The iterator pattern is one example. The iterator pattern also has some issues when you start trying to use it in network environments because the costs of getting the next element may be fairly high. We will see in later sections, in later modules of this course, how you can apply combinations of patterns, things like pattern compounds, to work around these deficiencies with individual patterns when used in isolation. But the most important thing to realize is that there's a lot more to patterns than just the information you get from the classic works of literature in the field. The Gang of Four book, the POSA 1 book, fantastic resources. I strongly encourage you to learn them, to apply them, to practice them over and over. But as you gain mastery over those basic patterns, you'll also start to want to apply the much richer set of patterns, especially the patterns that were intentionally designed for concurrent and network software. The link at the bottom of this slide provides you with some information about the broad range of additional patterns and pattern literature that's out there that you might want to leverage in your applications in the concurrent and network space.